we now want to talk about the concept of momentum. And we've already introduced the definition of momentum. Momentum is just the product of an object's mass times its velocity. Now we can write this in a somewhat more suggestive way involving forces. If we look at the definition of force, right, of course we know that force is equal to mass times acceleration, but in truth force is actually a little more general than that. We got this result, we handed it to you, but how was this particular result arrived at? Well, if I look at just the product of MV and I consider the overall change in the MV itself, right? So the change in MV over some time interval, if my object's mass is constant, then my mass can come out of the derivative, and I'm just taking the derivative of velocity with respect to time, and that is A. So a more general way of writing Newton's second law is that if I apply a force to an object, then that is going to cause a change in the object's momentum, and in the limit that my times become infinitely small, then my deltas become d's, and so I can write that force is equal to either a finite change in momentum divided by a finite change in time, or instantaneous change in momentum divided by an infinitesimal time. Okay, so F is equal to dp dt, and this is actually more what Newton actually wrote down as opposed to just ma. This is the more general case. And a very important idea that comes out of this, okay, a very important idea that comes out of this is the conservation of momentum. And the conservation of momentum is very closely related to Newton's third law. So conservation of momentum, I'll give it to you in words first, and conservation of momentum simply says when all external forces are acting on a system are zero. Okay, if the total net force acting on a system is zero, or in other words, if there are no external net forces. Okay, so if no external net forces, then P is conserved, is essentially what the statement says. Okay, if no external forces are acting on my system, then P is conserved. And we can see this. Let's consider the interaction of two billiard balls, say, and I'll call this billiard ball 1 and this billiard ball 2. And they don't both have to be stationary. They can both be moving, right? Typically in pool, one ball is stationary and you hit the cue ball into the other ball. We don't have to really consider that. Both of the balls could be moving, but when they collide, as long as we can ignore things like friction, external torques and things like that, which for billiard balls in truth we really can't, because of course there's friction and they're rotating and whatnot. But because those are extremely small effects that only come into play under certain circumstances, the most general case in billiards is that we can ignore those types of forces. So if I just consider these two objects and let's assume they collide, right? So for instance, maybe this ball is moving this way and this ball is moving this way, and they're going to collide. They collide, and when they move away from each other, their motion has changed direction, and probably their speed has changed as well. So if you change your direction and your speed, you have definitely accelerated. If you accelerate, you experience a force. So as the two objects collide, ball 2 is going to exert a force on ball 1, and ball 1 is going to exert a force on ball 2. And using the differential notation, what we would write is something like this: that the force that the second ball exerts on the first ball is equal to the change in momentum of the first ball divided by the time interval, and that the force that the first ball puts on the second ball is equal to the change in momentum of the second ball divided by the time interval over which the collision occurred. And notice in both cases, the deltas are the same. All right, the deltas are the same. And the deltas are the same, and Newton's third law says that for every force, there's an equal and opposite force. So if ball 2 exerts a force on ball 1, and ball 1 exerts a force on ball 2, then these forces must be equal and opposite. Okay? These forces must be equal and opposite. What that means is that the total change in momentum in the first ball must equal the total change, the negative of the total change of the momentum of ball 2. Okay? And what that means is, if I look at the total change in momentum, then it becomes 0. The total change in momentum is 0. In other words, no momentum was gained after the collision, and no momentum was lost after the collision. Another way of thinking about this is by looking at the definition of force up here. If the total net force acting on my system is 0, then that means that the derivative of my momentum with respect to time is 0, and any time that I get a result of 0 after taking a derivative, that means the object I was taking the derivative of was constant. And so if f is 0, then that means that 0 equals dp dt, and that implies that the total momentum is constant. Okay? So my total momentum being constant, my change in momentum being 0, meaning that no momentum was gained or lost, these two statements are equivalent. Okay? These two statements are consistent with one another, and that's what the conservation of momentum implies. Now we're going to, in the next video, look at a few more sophisticated examples of using momentum. Okay, we'll see you then.